Hi everyone, I'm Julian Lucek. I'm a distinguished SE at Juniper Networks, and I'll talk in more detail about the components of the Paragon Automation Suite. So here are the different components of the Paragon Automation Suite. So looking from right to left across this diagram, first of all, we have Paragon Pathfinder, which will play a starring role in the demos that we're going to show today. And Paragon Pathfinder has the ability to create traffic engineered LSPs. Those can be SRTE or RSVP-TE LSPs. And it can modify the paths of those LSPs during their lifetime according to observations made from the live network. And then we have Paragon Insights. That's our health monitoring system. It's capable of identifying faults in network elements and taking corresponding actions. Paragon Active Assurance is the solution for active probing across the network. It can send probes between POPs or from POPs to customer sites or from POP to cloud in order to ascertain the performance between different endpoints. And that can be in the form of parameters such as delay variation, and packet loss ratios. And then finally, we have Paragon Planner, which is an offline planning tool. And that's capable of taking snapshots of the live network from Paragon Pathfinder. And then with that snapshots, you can have a network model on which you can do exhaustive failure simulations or capacity planning. Now, all of these components are cloud native, Kubernetes based. You can deploy them on-prem, you could deploy them in the public cloud. And also, we recently announced that we're going to have a SaaS-based solution as well. What I'd like to do next is to show how the different components can interact with each other. So at the bottom of this slide, we have the network itself. And Pathfinder can see the topology of the network through the BGP-LS protocol. So that allows it to see the layouts of the links and nodes and attributes of links, such as bandwidth, SRLGs, and different types of metric. Also, Pathfinder can create traffic engineered LSPs via the PSEP protocol and modify them according to observed conditions or user input. Now, Paragon Insights is receiving streaming telemetry from the network in order that it can ascertain the health of network elements. And for automatic remediation, it can send requests to Paragon Pathfinder to create a maintenance on a faulty network element. Pathfinder can expose meshes of traffic engineered LSPs, and so you can choose to map a VPN to a particular flavor of LSPs. So for example, if you have a VPN that needs low latency service, you can map it onto the minimum latency mesh of LSP. Paragon Active Assurance is sending probes through the network in order to ascertain the performance between different endpoints, as we heard. And if the performance levels are violated, then Active Assurance can send an alert to Paragon Insights so that it can take actions accordingly. And finally, Paragon Pathfinder can create snapshots of the live network, and those can be passed on to Paragon Planner so that you can perform capacity planning and simulation in a network model that has been derived from the live network.
For the TE-LSP creation mechanism, you've got PSEP down there. Is there still a requirement for the netconf configuration pieces for pushing LSPs? At one point, when I looked at the previous version of this for Juniper equipment, it didn't actually provision via PSEP. It still used netconf to do that.
It's always supported both, actually. So from the outset, okay, both have been supported. So netconf can be useful if you've got legacy devices that don't support PSEP. So it's an alternative method that can be used. But in the main, people tend to use PSEP.
You know, I like that a lot, that it supported both, because in the transition mode, when we were deploying this in in a network, being able to use the netconf to really add PSEP as an alternative control on a pre-configured running LSP was a great option to transitioning the network over to complete path control on an existing large network, because we all know there's no such thing as a greenfield in service providers.
Yeah, that's very true. Yes, certainly the other thing you can do is if you have pre-existing LSPs that have been created on the ingress routers, via CLI config, you can actually delegate those to Pathfinder via PSEP. And so, if you turn on PSEP, then there's an extra line of config on an LSP to delegate it. And what delegation means is that PSEP message gets sent by the ingress router to the controller Pathfinder, saying that this LSP has been delegated. And from that point on, Pathfinder can alter the path of the LSP as needed, during its lifetime. So that's an alternative method of having PSEP, running with pre-existing LSPs.
We found that was a great feature to to do that, because when we first stood this up, you have thousands of services and LSPs out there, and just to be able to add that one delegation line to existing configuration with no service interruption whatsoever, and then all of a sudden you have the control, the central control, and the rerouting possible.
Oh, and the other thing is actually you can do the delegation from the Pathfinder side. So if you wish, you can have Pathfinder, add that extra line of config, for you in order to trigger that delegation.
Yeah, that's exactly what we did. We just had push the line
Perfect.
Out. The talk of the LSPs there is there was a whole lot of word soup or acronym soup that happened there. And for anyone that isn't totally familiar with LSP provisioning in SR networks, the terminology and the mechanism that we just described is essentially PCC initiated, PCE controlled, right? And I think it really shouldn't be understated, like Steve said, that the fact if you have an existing mechanism for provisioning LSPs, the command line or whatever it is, right? You already have an existing system, you can still use that while you transition over to using a segment routing controller, a PCE, and then just slowly transition each of the LSPs over. It's not a boil the ocean type scenario for a large network that has, maybe hundreds or thousands of LSPs already, that they don't need to do a flag day. Essentially, you can just delegate those existing LSPs and continue to use your old mechanism until you move over to the new one.
Absolutely, yes. I mean, one way of doing that is you could do it ingress router by ingress router. So you could say on day one, the LSPs of which this router is the ingress, those are the ones I'm going to delegate now, and then subsequently, another edge router, which is the ingress of some LSPs, those can be delegated and so on. So that's one method of doing it in a stage by stage way.
Yeah, that shouldn't be discounted. That's a pretty powerful feature set to be leveraged.
Well, and you even have the flexibility of using Paragon as the controller without actually provisioning anything from it. You can just use your existing provisioning system in all its glory and well-knownness to continue to push things out there and still have the LSPs controlled by Paragon, even though it created none of them.
Yeah, that's pretty much the migration strategy that I've seen every time.
So next we're going to see a demo of automated congestion avoidance. So we're looking at the same network as before, but this time I'm now showing the percentage utilization on each link. This information is derived from the streaming telemetry that the routers are sending to the Paragon automation system. And you'll note that the links have got varying amounts of traffic on them. And in particular, this one, which I'd like to highlight, the link between Amsterdam and Hamburg, in the direction from Amsterdam to Hamburg, has about 76% traffic loading at the moment. So far, I haven't turned the automated congestion avoidance on, because what I want to do is to turn it on in a few minutes so that we can see the difference before and after. Let's have a look at the paths of some LSPs that are passing through that busy link. So the LSP from Amsterdam to Prague is passing through that link, as you can see, as is the one from Amsterdam to Berlin. And so now what I'm going to do is to actually turn on the congestion avoidance. So I'm going to go into one of the menus. And so now I'm going into a settings menu. Normally one would have this turned on permanently, but we want to see the difference before and after. So I'm going to set a threshold here, and we are going to then submit that. And so this is a threshold above which we wish the Pathfinder to move some of the LSPs in order to bring the link below the threshold again. We here have applied it on a global basis, but you can also apply it on a more granular basis with a different threshold on each link if you wish. So while we're waiting for that to kick in, we'll see with the aid of some slides how the system actually deals with the congestion. So here's a diagram explaining how the scheme works. And of course, if a link gets congested to the extent that it's actually dropping packets, then clearly the customer's applications are going to suffer. So that's one of the motivations for having this congestion avoidance. The other motivation is from the CapEx point of view. If traffic is spread efficiently around the network in order to use the available nodes and links, then that delays somewhat the point in time at which you need to upgrade some of the links in the network in the face of increasing traffic over the course of the weeks and months. So let's see how it works. And so Paragon Pathfinder is receiving streaming telemetry relating to traffic. And that telemetry is of two different types. First of all, the routers are reporting how much traffic is traveling on each physical link. And then the ingress routers of traffic engineered LSPs are reporting how much traffic is entering each of the traffic engineered LSPs, of which it's the ingress. Because of course, traffic can only enter a traffic engineered LSP at the ingress router. And those traffic engineered LSPs could be RSVP LSPs, or they could be SRTE LSPs. And so in this example network, R1 is reporting how much traffic is entering the purple LSP and the blue LSP, and R4 is reporting how much traffic is entering the green LSP. Now, let's suppose that the link between R2 and R3 has reached the congestion threshold that we have set. Pathfinder can see that through the streaming telemetry. Also, it knows which LSPs are passing through that link that's reached the congestion thresholds that we set. And furthermore, it knows through the streaming telemetry how much traffic is traveling on each of those LSPs. And so Pathfinder has all of the information it needs in order to work out which LSPs to move away in order to ease the congestion. And of course, in so doing, it needs to make sure not to cause congestion elsewhere. So it takes that into account when making that determination. And then, having worked out which LSP to move, in this example, it decides to move the blue LSP. It sends a PSEP message to R1 because R1's the ingress router of that blue LSP. And that PSEP message contains the new path of the LSP. And so in this example, it's R1, R5, R6, R7. Because of course, it's Pathfinder that's determining the new path of the LSP because it's best placed to know what path to move it onto because it can see the traffic levels around the network. And so then R1 responds by moving the LSP accordingly. And so you can see that without any human intervention, the system succeeded in avoiding excessive congestion occurring on the link. So let's now go back to our demo setup, and we will look at the network topology again. And so now you can see a change. That link that we looked at before that had quite a lot of traffic has now gone down to about 43% traffic loading. And we can look at the paths of some of the LSPs that we looked at before. You can see that this one, which previously had been using that quite loaded link, has now moved onto a different path. Now it follows the path Amsterdam, Frankfurt, Prague. And so what happened is that the controller Pathfinder moved that LSP in order to bring that link below the congestion threshold completely without any human intervention.
When this system is kicking in, is it able to take into account whether or not there's a desire to keep things symmetrical with LSP pairs?
Yes, it does take that into account. So the symmetric LSPs would stay intact. That's true. Yes, that's right.
Okay, so it does the evaluation in both directions to make sure that the move is not going to cause a problem somewhere else as a result of that.
Exactly.
And the second question is this system also available for trending data so that you can see when you need to do upgrades or bandwidth upgrades for particular links, and when you would anticipate crossing thresholds?
Yes, you can look at traffic as a function of time on a given link. In fact, we could look at that now, or indeed on a given LSP. So for this LSP, we can look at how much traffic has been traveling as a function of time along that LSP. I mean, this one is fairly flat. And as you can see, as I hover this cursor, you can see what the traffic was at that point in time. But then you can do similar things for actual physical links as well within the network. So that's something else that you can do. In fact, so we could look at a link here by way of example. So here you can see traffic on this link as a function of time in each direction as well. And you can see that it dropped in the last few minutes after the congestion avoidance kicked in one of the directions. That's quite handy. Now, when it comes to capacity planning, as I mentioned, one can take snapshots of the network and import them into Paragon Planner, which is the planning tool. And that snapshot includes traffic levels. And so then in Planner, if you want to look at anticipated traffic over the next few months, you could apply a multiplier. For example, you could multiply all of the traffic by a multiplication factor of, say, 1.5 to see what effect that has. And with that increased traffic, one can perform exhaustive failure simulation to see that even in the face of the increased traffic, can the network, for example, survive a single link failure or double link failures and node failures, SRLG failures, and so on. So the two work quite well hand in hand when it comes to on the one hand, live traffic management within the live network, and also capacity planning looking into the future.
If I have SLA traffic that I'm carrying on those LSPs for various MPLS VPN services for enterprise customers or other service providers, how do you orchestrate that? How do you kind of plan for that? And how do you more specifically figure out when you've overcommitted your SLAs and say, hey, I have more traffic than I can move. I need to meet this latency target. I need to meet this, whatever this target is. And I can't move these because I'll violate SLA. How does that work?
Right. Yes. Well, when it comes to latency, that's a very good question, actually, because if, before the congestion occurred, presumably the low latency traffic is following the lowest latency path, because as you saw in the previous demos, Pathfinder can keep low latency LSPs on the path that is currently the lowest latency path. And so you don't want the congestion avoidance to divert such low latency LSPs away, because presumably the new path will be somewhat longer and therefore have higher latency. And we can ensure that, in fact, the way the congestion avoidance works is that, first of all, it considers as candidates for moving the LSPs that have the worst priority level, because an LSP can have one of 8 priority levels. And if there's no suitable candidate within that worst priority level, it will move to the next one and so on. And so if you wish low latency LSPs not to be moved by the congestion avoidance algorithm, then you can give them the best priority level. So they'll be the last to be considered as candidates for moving them. So they tend to stay onto the current, presumably lowest latency path.
The priority level, is that an arbitrary value that is assigned by the controller? Is there a mapping to experimental bits with that? How does that work exactly?
That's a value that you can set on the LSP, either at creation time or subsequently. So it's literally a sort of value ranging from 0 to 7 that expresses the priority level.
Are those levels mapped directly into queues?
Not necessarily. You don't have to actually have a mapping between priority levels and queues. It's more related to preemption and hold priorities. If at the end of the day there's insufficient bandwidth to carry LSPs across the network, then the priority level determines which ones get access to the network capacity, and also has a bearing on the congestion avoidance algorithm. But it's not necessary to have a mapping from that into queues necessarily.
Okay.
Yeah, I'd like to think of that more as a controller level priority rather than a class of service type of thing.
Exactly. It's more to do with the behavior of the LSP as a whole. That's right.
Okay. So that is specific to the controller and not necessarily, there's no prerequisite to have specific class service queues that map directly into those. Is really
correct.
distillation
Correct.
of what you're saying.
Correct.
Thank you.